Okay, in this video, we're going to talk about the correlated groups t-test, which is also called a dependent samples t-test, or sometimes you might even see a variant of it called a matched samples t-test, but we're going to use the term correlated groups. So we use this when observations in two samples are related to one another in some way. In other words, the scores are not truly independent of one another, and it kind of makes sense to pair scores across samples. So we need to develop a statistical test that recognizes that observations across samples have a relationship with one another. And that's going to require the creation of something called a D-score, and I'll show you how to do that in just a moment. But the D-score is the difference between two scores that are in fact paired together. So when do we run a correlated groups t-test? When there are two groups or samples. So we start with two samples. We're actually only going to run the analysis on one sample, which is a new distribution essentially that we create. And we're going to treat that as almost like a one sample t-test. But the observations across the two samples that we collect are not truly independent of one another. There's some relationship between members of the groups such that the observations, in other words, the scores, can be paired together legitimately. So let's take a look at our amazing statistics selector. And again, we ask the question, how many samples do we start with? Well, in this case, we're going to start with two. Now, if we had one sample, of course, we would do a z-test for a sample mean or a one sample t-test, depending on whether or not we knew the population variance. And if we had more than two samples, then of course we would do what's called analysis of variance, and that's coming in later videos. But if you have two samples, really the only question left is, are the groups independent of one another? If there's random assignment, you know right away that they are independent of one another. And so if the answer is yes, we'd do an independent groups or an independent samples t-test. It's called either one of those two. But if the answer is no, that the groups are actually dependent or correlated, then we run what's called a correlated groups t-test. Again, it's also called a dependent samples t-test, depending upon your text. So how can groups be correlated? Well, there's really three kinds of relations that we're looking at here. The first is when we measure growth or change over time in the same individual. So for example, we could look at height of children over a 3-year period. That would be a within group measure of variation. Now, for a t-test, there are only two levels of the independent variable. So we would measure now and then again at 3 years. Okay? It doesn't have to be that long of a period. It could be a test-retest paradigm, for example, where we do a pretest of an individual, some sort of intervention, and then we test them afterwards to see the effect of the intervention. That would count as well. When participants or observations are related. So for example, there may be a familial relationship, fathers and sons, mothers and daughters, brothers and sisters, maybe bosses with employees, or two individuals from the same neighborhood, but there's some relationship between individuals such that they could be paired together. One person would be in one sample and the other person would be in the other sample, but they'd be matched together to create the D-score. Or when the same participant provides more than one score or rating. So that would be the case with judge ratings, or perhaps scores for the same participant in different domains. For example, if we had a test score for the same person in an English class and a test score in a philosophy class, and we were looking to see if there were differences between the two. Okay, as I mentioned earlier, the calculations here are actually fairly similar to a one sample t-test. Such that the steps are about the same. You'll see some differences in the terminology and notation, but for the most part, what we're going to do is create a new score, a D-score, and then use that distribution to run the test. So it's a tweak, and the tweak is that we create the D-score. It's called the difference in scores. D stands for difference, and it's just the difference between paired observations of scores. So this is going to be similar to a one sample t-test. Now let's take a look at how it might be different from an independent groups t-test. With the independent groups, for example, let's imagine that we were doing a quiz And we were simply looking at how many answers an individual got correct after a lesson plan, and 10 is a perfect score. Okay, and let's say that one group, they were given a multimedia lesson, and the other group had, say, a regular lesson from an instructor in a classroom. Okay, so the multimedia lesson group might be group 1, and the lesson from the instructor might be group 2. Now, every cell here, every value that you see is going to represent an individual and unique participant. So in this case, the n is 10 for group 1 and the n is 10 for group 2. Now, obviously, we would then sum the scores for each group and then compute the mean. Now, when we do the independent groups t-test, the means for each of the group are then compared to see if there is a statistically significant difference between the two groups. In other words, whether those means are more than what we would expect due to the difference between them is more than what we would expect due to sampling error. So the level of analysis is right there in the green box, right? That's the difference between the mean of x sub 1 and the mean of x sub 2 is going to be what's in the numerator of the t ratio. Now, a correlated groups t-test is a little bit different. You'll notice, first of all, that in this case, we're a little bit more efficient and economical in our participants. We're going to be looking at a particular type of correlated groups t-test that involves simply a test and a retest. Okay, so if you imagine that we now have 10 participants, and then we're going to pre-test them to see their knowledge on a quiz, for example, prior to perhaps giving them a video lecture. And then we will post-test them or do a post-assessment. Okay, so there's our pre-test or pre-assessment scores and our post-test or post-assessment scores. And then the analysis actually involves a new distribution that we're going to create where we're going to subtract the scores from one variable from the scores of another variable. Now, we could either do this as x sub 1 minus x sub 2, which is what you would probably normally do. But if you're expecting scores to increase over time, it makes sense then to do x sub 2 minus x sub 1 because that'll yield positive values. So I just flipped x sub 2 and x sub 1. And in this case, we end up with values like this. So for example, for the first participant, their score pre-test was 5. The score on the post-test was 8. That's going to yield, if we do x sub 2 minus x sub 1, a D score of 3. In other words, the individual score went up 3 points on the post-assessment. Again, it doesn't really matter whether you do x sub 1 minus x sub 2 or x sub 2 minus x sub 1. That's only going to change the sign of the D score. It's not going to affect the analysis in any other way. And generally, you'd like the sign to be consistent with conceptually what it is that you're measuring. Now, in something like this, where the point of, say, a video intervention on a lecture is to increase knowledge, it makes sense to do x sub 2 minus x sub 1 to create the D score. In other cases where you're simply matching individuals who are related together, there may be no reason to do that, so you could just do x sub 1 minus x sub 2. Okay, so then what we're going to do is we're going to sum up all of these D scores, and in this case, we're going to get a sum of D equals 26, and then the mean of the D scores is 2.60. Now, if you think about it, if the null hypothesis is true, then there should be no effect over time, and the mean of the D scores should equal 0, right? So the null hypothesis is going to state that the mean of D is 0. Now the question is, in this case, this example, is a mean D of 2.60 greater than 0 to a degree that we would expect more than could be accounted for by sampling error, okay? So again, we're going to need some measure of sampling error. And to get that measure of sampling error, we're going to look at the standard deviation of that D distribution. And then we're going to use that standard deviation to compute the standard error for the correlated groups t-test. So again, the steps are going to be a little bit different from what you've seen before, but ultimately we're always trying to figure out what is our measure of standard error. right? And in this case, the standard error is going to refer to the amount that we expect those D scores to deviate by chance or sampling error. Okay, so advantages of a correlated groups t-test. First of all, they're more powerful, and there's a long statistical explanation for why, but it basically boils down to this. Between groups designs introduce individual differences as a source of error variance in scores, and that creates noise. So it makes it a little bit harder to detect true effects in the statistical test. So if I have a whole bunch of folks who are randomly assigned to one group and a whole bunch of folks that are randomly assigned to the other group, they differ in a couple ways. One is that one group, gets a manipulation of the independent variable, or one level of the independent variable that the other group doesn't get, but they're also just different individuals, right? So they bring in their own histories, they bring in any of a variety of things that could essentially be a nuisance in terms of determining scores on the dependent variable. Okay, we'd call that a disturbance variable. So those individual differences in backgrounds, which could affect scores on the dependent variable, aren't present in the correlated groups t-test, because if the same person is tested twice, there are no individual differences to consider. So there's no individual differences disturbing the data. So that means there's more power, which in turn means you can have probably smaller sample sizes in order to run the study, and that makes them more economical because research participants cost money, right? So it's a more economical study. Okay, big picture, the correlated groups t-test is used when observations are related in some way. It's also called the dependent samples t-test, so either of those terms is used. There are two samples, but the analysis is conducted on a distribution that is created by subtracting the score of the second sample from the first sample. Okay, and that of course is called the D score, or difference score. And its values represent the difference between paired observations across our samples. Now, the correlated groups t-test is more powerful than the independent groups t-test because individual differences are removed essentially as a nuisance variable. Okay. All right, so the next step is we're actually going to walk through the steps and conduct a correlated groups t-test by hand.